My name is Ashley Keene, and this is my Lab 1 presentation on charged tapes for Physics 2212. The intention of this lab was to observe interactions between two charged pieces of clear tape to become familiar with physics principles of charge, electric force, and excess charge. Additionally, we want to see the interaction between these two charged pieces of tape. To do this, we started by charging two pieces of tape by creating a length of tape and pulling it from another piece of base tape to allow electrons to move from one piece to another, and did this for two pieces of tape to create two pieces with equal charge. We also created a setup that looked like the figure below and to the right, and by moving tape A towards tape B, they would repel each other because they have the same sign of force, and we were meant to record the distance at which tape B begins to float. Here are some important physics principles and equations that we need to know for this lab. The first is the equation for the force due to gravity on tape B. The second is that the electric force on B is equal to the charge of B times the electric field of A. The electric field of A is equal to Coulomb's constant times the charge of A over d squared, where d is the distance between A and B. Assuming the charges of A and B are equal, we can see that the electric force is equal to the charge squared times the electric field of A. We also know that for the tape to float, the force of gravity has to be equal to the electric force on B at that moment, since there's no acceleration at the moment that it begins to float. And so to sub for both equations, we can see this equation for charge. To make these calculations easier, we can assume that there's no air resistance in this model, that there's an even distribution of charge on each tape. Both tapes have the same charge, and we can also say that the location of each tape is at a point charge at the center of each location of the tape in the observational model. Here's some information that we're also going to need to know to compute those equations. So the first is that the length was 20 centimeters. Second was that the mass of this tape was 2 times 10 to the negative 4th kilograms. And third was that the observed distance to float was 0.005 meters between A and B. Also, on the far right, you can see an FBD of the red point, which is tape A, and the blue, which is tape B, and this shows the forces on tape B at the moment that it starts to float. Now I'm going to talk about my computational model for this situation that I created using GlowScript. Here are some of the constants and measurements that I talked about earlier. K is Coulomb's constant, which is 1 over 4 pi epsilon naught. Here's some things that I coded for the setup and the forces. So you can see on the top right, I have the force due to gravity, which is equal to the mass of the tape times the gravitational constant, and the electric force is equal to the opposite of that. I also set up the locations for both A and B, where A is at the origin and B is at that distance right above tape A. And here are some of those coded calculations for the charge, the electric field, and the electric force. And here's the output of that GlowScript model. So you can see that the charge of each tape is 2.33 times 10 to the negative 9th Coulomb. The electric field at B due to A is 8.40 times 10 to the 5 newtons per coulomb. And the force of gravity is equal to the electric force on B due to A, and both of those, the magnitude is 1.96 times 10 to the negative 3 newtons. So here I talk a little bit about the excess or deficit of electrons, and in order to do that, there's a couple of things we needed to calculate. So first was the number of electrons on the tape, which was equal to the charge of the tape, which was calculated in GlowScript, divided by the charge of electron. And I found that there was 1.46 times 10 to the 10 electrons on the tape. Then I calculated some information about the atoms that lost electrons using the cross-sectional area of the atom, which was using the radius and comparing that cross-sectional area to a square, and found that ratio was 2.6 times 10 to the 7th. We can interpret that as one atom in the tape lost an electron while being charged for every 2.6 times 10 to the 7 atoms in the tape. This means that the tapes were positively charged, which was shown in the computational model. It makes sense since both had the same sign of charges and repelled each other. So here's the first question for this lab with a little bit of connection to the physics principles, and it's asking about if the electrons had positive charge and the protons had negative charge. In this situation, still the magnitude of the charges would have been equal. They would have just had opposite signs, but still each tape would have had the same sign and would have still repelled each other. Finally, the last connection question was, why is it important to handle the charged tapes as little as possible? And this is important because our hands are neutral, and while handling the tape, it means that charges could dissipate over our hands, which would mean that the magnitude of the charge on the tape could decrease.